Alright, here we're at section 14.3, which is the ideal gas law. And when we're talking about ideal gases, we're talking about things that fit perfect. And we're going to include moles here. So we're talking about getting this all to work just right. And we're including our variable n. Usually that's written as a little n. Remember that the number of moles is directly proportional to the number of particles, and that's directly proportional to our volume. In other words, 1 mole, remember, 22.4 liters. So if I doubled that, obviously that's going to directly affect this. It'd be 44.8 liters. That's what we're saying. Directly proportional there. Alright, so here's my formula. If I have P1 times V1 over T1 times the number of moles, because that makes the difference. So I'm factoring that in. So this is the combined gas law plus we've included n. N being the number of moles. Now, let's assume that on this one we put everything at standard things that we are familiar with. Another standard pressure, 101.3. The volume, 1 mole, well, therefore it would be 22.4 liters, and standard temperature. So we substitute in all of those things that we know. And so we're going to take this and we're going to replace it with a value which we call R. And if we calculate that out, we get this number, 8.31. So that's how that number comes to be. And I know we've used it a little bit in the popcorn lab, but this is how this number comes out, 8.31. It comes from putting in everything into this equation that we would know as standard temperature, pressure, and 1 mole. If we do that, we can now solve this equation. In other words, we took all this and said, hey, make that R. And then this was, really what it was P1 V1 over T1 N1 should be a little n, N1 equals R. We don't need the ones because in this you can see there's no 2's. We've gotten rid of it all. So if I multiply, cross multiply, this is over 1, cross multiply that times that, I get PV equals nRT. So this is my ideal gas law. So really, so far we have, while we have 3 laws before the combined one, really all you got to do is remember the combined gas law, PV over T, and then the ideal gas law. Those are the main 2. Take a look at page 427, and let's work through a problem on that page. It says a deep underground cavern contains 2.24 times 10 to the 6 liters. So that's volume. Volume 2.24 times 10 to the 6th liters of methane gas at a pressure 1.5 times 10 to the 3rd kilopascals. 1.5 times 10 to the 3rd kPa. And a temperature 315 Kelvin. How many kilograms? So we want to know mass. How many kilograms? We don't know that. Does a cavern contain? Well, while we don't know kilograms, we do know or can calculate N, which is moles. And for moles, I can convert back to grams or kilograms. So we're going to use the ideal gas law. PV equals nRT. We know P, V, and we know T, and R is a constant, so we can solve for N. So we're going to put in all those things that we've got there. So 1.5 times 10 to the 3rd times volume 2.24 times 10 to the 6th equals my unknown number of moles times 8.31. And it's a really weird label. It's liters times kilopascals over Kelvin mole, which means everything else cancels. And my temperature is 315 K. Yeah, I'm not putting those in right now. So now I can just calculate that out. So I'm multiplying this times this and dividing by these 2 here, and I end up with N equals 1.28 times 10 to the 6 moles of CH4. It said methane, CH4. Now, if I want to convert that to grams, I'm going to use the molar mass. So how many grams do I have? 1.28 times 10 to the 6th moles CH4. And every mole of CH4 is 16 grams. And multiply that out, and I would get 2.05 times 10 to the 7th grams. I want to convert to kilograms. I need to divide that by 1,000. So, take away 3 from that, so it would be 2.05 times 10 to the 4th kilograms, or 20500 kilograms. Okay. All right. That is pretty good. Let's take a look at this one last graph here. Actually, I guess there's a couple things, sorry. First of all, there's a couple things to understand. One, ideal gases don't really exist. No such thing. But this law allows us to do a lot of calculations, which is nice. At many conditions of temperature and pressure, these are pretty good. It's when you get to extreme ones, really high pressure, really low temperatures, things like that, then you have some issues. So at low temperatures and high pressures, the ideal gas law doesn't work well. Take a look at the next page. All right, so you can see, when we're down here, and I mean, look at this. This is 20,000 kilopascals. We live at 101. So, our stuff that we experience is usually down in here. And at that point, it's pretty close. But as you get farther away, you can see that those things get off by quite a ways. But when you keep them in relatively normal circumstances, the ideal gas law works pretty well.